video is uploaded from the 27th.
Okay.
It might not be. I know that there's quite a few things that's missing in between, like the reading quizzes. He said that he was going to try and get them going when they were not buggy anymore, but they've been buggy, so he didn't really want to post them until they weren't. And so I don't know if maybe
can you guys hear me? Is this better?
Yeah, a little bit. There we go.
A little bit. Am I still roboting?
No, you're better now. At least for this minute.
Oh my God.
Much better.
How infuriating.
Yeah, I can hear you now.
Not pixelated anymore.
The video from the 27th should be posted. Let me check.
Yeah, I missed that
It
one
is
too.
not posted. What is going on? All right, so while we're recording, I am not going to take the time to try and troubleshoot the video from the 27th. That is so frustrating.
And then I do have a quick question that might be a little bit more frustrating as well, is are there going to be reading quizzes for chapter 13 and 14?
Well, since we're having an exam over chapter 13 and 14 like tomorrow, it's probably not even worth the time, since the reading quizzes are just to be like sort of a help. I tried to put a lot of questions from 13 and 14 onto the practice test so that you would have some example kinds of questions.
Okay.
I'm just really disappointed in the performance of Canvas with the reading quizzes, because I'll take them and then I'll take them again 10 minutes, like I'm filling in the answers, and I get 2 different scores back when I take the same quiz 2 times, and I don't know what is going on with them. But they've been more frustration than an actual study aid, because I mean, Orlina, you take them and you're like, I got all those questions right, and I know I didn't get all the points, and that makes you second guess like what you know to be the truth. And I don't want people to like be less confident in their own correct answers because of a tool that I'm giving them. So I'm still trying to figure out what's going on with them, but why don't we try and like re-begin reading quizzes with chapter 16, and hopefully I can get the chapter 16 one to behave correctly.
Okay. I mean, if not, you could always just send it my way first, and then I can let you know.
Yeah, I just don't, I want the quiz to be something that is affirming, not something that is like frustrating. You know what I mean? It should only be frustrating if you really don't know what you're doing. And that is good frustration, because it'll cause you to seek out additional help and resources to figure out what you're not getting out of the material. But that's not how they were behaving.
Annika, I was looking through to see if I could find the exact PowerPoint page on 14. It's the PowerPoint slide that's 24. It looks like that.
Oh, okay, thank you.
And then I actually wrote in like the PCC and everything. I don't remember exactly what video it is, but on one of them, he actually goes through and says that PCC will create or go to like one reaction, but it won't go to the other. But then you go for the Jones reagent and it will make it all the way to the end of it. So that's really helped me on like understanding the reactions of the alcohols.
Thank you. I'll go back to the PowerPoint.
Yeah, and so PCC is not in your textbook. That's something that I've added. And the reason why is because if I'm teaching you an introduction to organic chemistry, one of the things that's important for us to learn is that the same functional group can sometimes be turned into different things depending on what reagent we use. Emma, can you mute yourself, please?
Yeah, sorry.
No, it's okay. I think that was the Ghostbuster sound that I was getting.
When you say that different reagents can be used to get different products, that has a lot to do with whether or not you're dealing with primary or secondaries as well for what.
Yeah, I mean, not always, right? So basically the difference between PCC and Jones reagent is like an example of the fact that sometimes we can control how much we oxidize a carbon, depending on which reagent we treat it with. And that's not something that you would have learned if you had just learned about Jones reagent, like the nuclear bomb of alcohol oxidizing agents. So Jones reagent is like the one, like, if it can be oxidized, Jones reagent will oxidize it as much as it can be oxidized. It's the nuclear warhead of oxidizing agents for carbon. Well, there are some, never mind. All right, yes, that's probably a good characterization.
So just a guess, Jones reagent is probably very toxic.
Well, it is, but not because it's a strong oxidant. Like, for example, over-the-counter bleach in solution is a very strong oxidizing agent. Hydrogen peroxide is a very strong oxidizing agent. The reason why Jones reagent is super toxic is because of the chromium in it. So I don't know if it's kind of dated now, but if you've ever seen Erin Brockovich, the movie Erin Brockovich, anybody ever see that movie? So they talk about hexavalent chromium in Erin Brockovich. That's chromium with an oxidation number of 6. That's the same oxidation number that chromium has in H2CrO4 and K2Cr2O7. So yeah, chromium with an oxidation number of 6 is really toxic. And chromium in general is pretty toxic anyway. It's a heavy metal.
Okay.
All right, let's see if we can maintain our connection even while I'm sharing my screen. You have a what question?
I have a minor question.
Okay.
It has to do with pronunciation. For an ester or an is it an alcohol? No, aldehyde. Oh, I'm getting them now. Basically, if it's an alcohol versus an aldehyde.
Okay.
Just in speech, it sounds really similar when you hear it quickly, even though you know it's spelled differently.
Oh, are you talking about in systematic naming?
Yeah.
So there are a couple of differences. All right. If I was naming that alcohol, that is a 3-carbon long alcohol. All right. And the OH group is at carbon 1 of the chain.
Mm-hmm.
And this is a great bridge because we have to talk about naming of aldehydes and ketones today, even though naming of aldehydes and ketones isn't on exam 1. All right. But in the long run, there is a little bit of similarity in the names here. What if instead of 1-propanol, and remember the 1 is the locant for the alcohol functional group here, right?
Mm-hmm.
What if instead of an alcohol, we had an aldehyde at carbon 1 there? In that case, the correct name, why is that heart-shaped? I think we're coming up on Valentine's Day. Oops. The correct name there would just be propanal. Now, why on earth do we not have to use a locant for the aldehyde functional group? Can you think through that just a little bit and think about why you might not need a locant for the aldehyde functional group? So remember, we're assuming that the aldehyde is the only major functional group in the molecule. Why would we not need a locant for it?
Do you want the answer?
Sure.
Because it's always on the end, so it's always going to be on the 1 anyway. Because if it was in between 2 carbons and not on the end, then it'd be a ketone.
Right. It's always on carbon number 1 of the main chain. So the way that we name things with functional groups is we find the longest chain that contains the functional group. All right. So if the aldehyde is the functional group, it's always at the beginning of that chain. There's never a reason for us to give a locant for that functional group.
Okay. My question was more on the enunciation of the suffix.
1-propanol, propanal.
So you make it kind of a harsh now.
Yeah, I do. Yes.
I was reading it in my head and I realized I kept saying propanol. And I was like, wait, that sounds like it's an alcohol and it's not. How are we supposed to pronounce it? So I was wondering.
So the al comes from aldehyde. So I use the same enunciation for al as I do for aldehyde. And
Okay.
that's how I pronounce it.
Okay.
All right, so we're already into talking about naming of aldehydes and ketones. So let's do that. And I'm going to see if you guys can figure out the correct name for this aldehyde. It looks complicated, but it's not that bad.
No, I'm laughing at the heart again.
Yeah, I don't know what's up with that. So what is our longest carbon chain that contains the aldehyde functional group?
Is it propane? No. What's 4 again? Butanol?
Well, it's not 4, so that's the first problem.
Is it, oh, never mind. Those aren't benzene rings. Never mind.
Those 2 carbons are the only carbons in the main chain. The others are all part of rings. Remember, each carbon has to be either part of a ring or not part of a ring. It cannot be both. So our longest carbon chain is only 2 carbons long, which means that these 2 substituent groups are both at carbon 2 of the main chain. So a 2-carbon alkane would be ethane. A 2-carbon aldehyde would be ethanal. So since we have ethanal with a couple of cyclohexane rings at carbon 2 as substituent groups, this would be 2, 2 dicyclohexyl ethanal. Does that make sense, everybody?
Mm-hmm.
So naming aldehydes is easy. And the reason it's easy is because we don't have to even use a locant for the aldehyde functional group. From there, we just have to identify and give locants to any other substituent groups that are on the molecule.
For these chapters, do you think you can put up the PowerPoints for them as well?
Very soon, Orlina.
Okay.
Yeah, I'm almost done with the PowerPoint for chapter 16. I just haven't finished like editing. All right. There are a few like little things that I have to cut out of it because I stumbled and repeated myself and I don't like looking dumb on my videos.
Well, like the PowerPoints like you did for 11 through 14.
The PowerPoints. Yeah. I can do that tonight for sure.
Okay, awesome. Thank you.
Yep. So I'll have the PowerPoints up for 16 through 19. The stuff for, I think it's 16 through 19. It's exam 2. I'll have all the exam 2 PowerPoints up tonight. Okay. So we've named some aldehydes. The suffix that we use is al. All right. So propanal, ethanal, methanal, butanal. For ketones, we use the suffix "-one" instead. All right, that makes perfect sense. Don't worry for this class about having more than one aldehyde functional group on a molecule. All right, we're not going to have dials to worry about in here, even though it is possible to have that in a molecule. So I'm going to give you guys a couple of ketones to name and see if you can figure out how to name them. It's always much, much easier to figure out naming by just naming some examples and then seeing how the names are put together, especially now that you know most of the rules for how naming works. I don't know what's up with my curvy bond here. I wish I could erase that, but I can't. So just deal. That's a cyclohexane ring with a carbon-carbon double bond on it. All right. So if we didn't have any substituent groups on that ring at all, what would we call that? So if it didn't have the carbonyl group on it, we just call it cyclohexane, right? With the ketone on it, we would call it cyclohexanone. So what are we going to do with those substituent groups? All right, so that's a cyclohexanone with some substituent groups on it. Looks like we're counting in this direction to get to our first substituent group as quickly as possible. So we've got a methyl group at carbon 2 of the ring, a chloro at carbon 3, and another methyl at carbon 4. So we alphabetize, and chloro comes before methyl. So 3-chloro, and then 2,4-dimethyl. Remember, we have to say how many if there's more than one of a substituent group. And then we name the ring, which is a cyclohexanone. Note that I didn't have to give a locant for that ketone that was part of a ring. So why not? We're assuming that if it's a cyclohexanone, the ketone is at carbon 1 of the ring. All right. So what about here? We've got 2 ketone functional groups. And if we get to the first one as quickly as we can, that probably means we're counting from this side of the main chain. 1, 2, 3, 4, 5, 6, 7. So if there was only one ketone in that chain, we would call it a heptanone. Since there are 2, we could call it heptane dione instead, to say that there are 2 of those one functional groups. We've got an ethyl group at carbon number 3, and our ketone functional groups are at carbon 2 and 5 of the main chain. So I would name this 3-ethyl, and then 2,5 heptane dione.
For that molecule?
Yep.
Or, you would always choose the carbon chain that would include both of the ketone functional groups. So even
Yep.
though there is a carbon chain that's 7 long that includes a ketone,
Exactly.
you would choose the 7 chain that includes both of them.
Yes, yes.
Okay.
So in general, the reason for that rule is that we want our substituent groups to be as simple as possible and not contain more functional groups in them. So by numbering in a way that both of those ketones are part of the main chain, that leaves us with a much more simple ethyl functional group instead of a functional group that actually contains a ketone as a substituent group.
I have a question.
Sure.
If the ethyl group was an ethyl alcohol or an ethyl aldehyde?
Don't worry about it.
Oh, okay.
Then you're talking about a molecule that you might name in majors level organic chemistry. Or maybe if you're lucky enough to have me for majors level organic chemistry, I'll say let a computer name it when there are enough different functional groups all together in there, because it gets to be a pain in the butt. So there's an order of operations where you go from most important to least important functional groups in terms of prioritizing how you name what is part of the main chain and what's a substituent group. And it's really hard to remember, because literally you have to remember the order of operations for every possible organic functional group, and there are a truckload of them. So it's not worth it. Naming is important, but it's not that important that we should spend all of our time worrying about it. So if it has more than a couple of important kinds of functional groups, so things like halides are really easy because we always name them as substituents and not like the important functional group of the molecule. But if there's more than one important type of functional group, like an aldehyde and a ketone and a carboxylic acid, it's really hard to know how to name those kinds of molecules. So there are computer programs that can do that. We don't have to worry about it. It's much more important to know how they react than to know how to name them, because computers can do that part for us.
Okay.
All right, let's try one more together. How would we name that ketone?
It's a long one.
It's not that bad. So if we're looking at the main chain, hopefully you're counting 4 carbons in the main chain.
Yeah.
Okay. And that means that we're talking about a methyl ethyl propyl butyl. So this would be butanone. All right. Butanone would be the parent name. And what substituent groups do we have attached? We have a cyclopentyl group attached at carbon 1 of the main chain. We have methyl groups, 2 of them attached at carbon 2 of the main chain. All right. So cyclopentyl comes before methyl alphabetically. So I would have this titled 1. Okay, maybe it is a little bit of a long name. 1 cyclopentyl, 2, 2 dimethyl. And remember that we do have to talk about the position of the carbonyl group here, of the ketone, because the ketone theoretically could be at any one of these 3 carbons of that 4-carbon chain. It can't be at the end because then it would be an aldehyde, but it is at carbon 1 of that 4-carbon chain. So we call this 1-butanone.
I have another question.
Yep.
Does the cyclo count for alphabetizing, even though
Yes.
the di-tri doesn't
Yes.
count?
Yep. And if somebody did everything right except for they got it out of alphabetical order because they couldn't remember about the cyclo prefix and whether it counts for alphabetizing, then I wouldn't take that as an incorrect answer anyway. That's a trifle.
Got it. So if it will, okay.
Because that's what I got, because I alphabetized it from like the pentyl
Yep,
portion
it's-
of it. And
Yeah,
so like,
cyclo counts, but di and tri don't.
it.
Isn't that weird?
Okay.
Anyway, that's a trifle. That's not really that
so,
important.
but
If we put those out of order, any chemist would still be able to write that structure from the name, even though the substituents were not in alphabetical order based on the parts of the alphabet that were important and not important. So yeah. Remember, don't shoot the messenger. I didn't make up these rules. If it was me, whatever the prefix was, whatever was at the beginning of the thing that we're putting in, that's what I would use to alphabetize so it's consistent and easier to remember. But I'm not the person that made up the rules. So I'm just trying to tell you how to do it.
Okay.
Very much like thiols and ethers. What are some other functional, and halides? Aldehydes and ketones are polar. With very few exceptions anyway.
That has to do with if they have extremely long carbon chains with only, say, one.
No, it
ketone.
has to do with whether they're symmetrical. So sometimes we could potentially have 2 carbon oxygen double bonds that were 180 degrees apart from one another so that the bond dipoles canceled one another out. And then you could potentially have a diketone that was nonpolar, even though it had polar bonds. But almost always, aldehydes and ketones are polar, and just like thiols and ethers and halides, they cannot hydrogen bond. All right, so they have dipole forces, the middle kind of intermolecular forces.
The oxygens that are parts of the aldehydes and the ketones.
Yep.
They can't hydrogen bond to, say, like a water molecule?
They can. So when I say they can't hydrogen bond, what I'm saying is they can't hydrogen bond with themselves. When they have intermolecular forces with themselves, they have dipole forces. All right.
Okay.
So this is the section of the book where we talk about the kinds of intermolecular forces that aldehydes and ketones can have. So something like acetone, that's a common name for this. All right. There are some small aldehydes and ketones that have common names that are so common that nobody uses the systematic name. So when you go to the hardware store and you need that solvent, you call it acetone. What would we call it if we're calling it its systematic name? Two-propanone. Nobody calls it that at the hardware store. They call it acetone. All right. This is the shortest aldehyde that exists, a 1-carbon aldehyde. This is formaldehyde. So in aqueous solution, that's what's used to embalm dead people and dead critters, whatever. Now, because of the very polarized carbon-oxygen double bond, small aldehydes and ketones are very soluble in water. And the reason why is because they can share hydrogen bonds with water, right? They don't hydrogen bond with themselves, but they can share hydrogen bonds with water. So small aldehydes and ketones like these, your book says up to 6 carbons, but that's kind of BS because 6 carbon big aldehydes and ketones are only very marginally soluble in water, all right? But small aldehydes and ketones like these are actually miscible with water, which means that we can mix them with water in any proportion and they'll dissolve in one another. So when we talk about solubility, it's one of the things that students always like a firm answer, like, is it soluble or is it not soluble? And that's not really the way it works. It's like a sliding scale, all right? So when you dissolve sugar in water to make a solution, we would say that sugar is soluble in water because we can dissolve a metric ton of sugar in water, all right? But what about if we could only dissolve like 1% of a solute in the solvent? Is it still soluble? Yeah, all right. If you look at in books, when we talk about solubility, very often references will talk about things being sparingly soluble, which means it's only a little bit soluble. So in general, what I want you guys to know about the solubility of aldehydes and ketones is the bigger the molecule is, generally speaking, the less soluble it'll end up being in water because it will have a lot more hydrocarbon and a lot less of the aldehyde or ketone polarity to it. So these would be very, very soluble in water, but something like 2-octanone would not be very soluble in water at all. So I should probably write down what I've been saying about the types of intermolecular forces that aldehydes and ketones have. We call those dipole-dipole forces, the kinds of intermolecular forces that polar molecules share with themselves. All right, but because of those oxygens in the aldehyde and ketone functional groups, they can share hydrogen bonds when they're mixed with water. Question?
I have a side tangent question, maybe.
Okay.
My last chem teacher taught the intermolecular force bonds that ionic bonds are on that all the intermolecular forces are on like a spectrum. And
Okay.
so on one end, you actually have ionic bonds as a type of intermolecular force, such as in lattice structures. And they're actually the strongest, followed by hydrogen bonds, followed by dipole to dipole, and then last the van der Waal or London dispersion ones.
So I don't consider
I feel like it's contentious because different textbooks either do or do not acknowledge ionic bonds as.
yeah, you're trying to start a fight right now, Ariana, is what you're trying to do. You're trying to start a fight.
Okay, that's what I was wondering, is if it's.
So we're worried about the kinds of intermolecular forces that happen between uncharged compounds right now, okay? Later on, we will actually add to the palette a little bit and we'll talk about the attraction between an ion and a dipole. That happens sometimes. It's really important, particularly when water dissolves things. So if we talk about the attraction between a chloride ion and water, that is the attraction between the positively charged dipole of water and the negative chloride ion. Those are what we call ion dipole attractions. So are they intermolecular? Well, that Cl- isn't a molecule. So the term intermolecular is a little misleading. When we talk about an ionic lattice, those are ions, they're not molecules. So that's why I don't refer to them as intermolecular forces.
That makes a lot more sense than how she explained it. Okay.
Yeah.
Okay.
There's always a reason behind why I do what I do. And sometimes the reasons are capricious and arbitrary, like somebody else decided that this is the way we alphabetize those names, right? But there's actually a good reason for me leaving ion dipole and ion-ion attractions out of our list, because they're not really molecules most of the time. So sometimes ions can be part of an organic compound can be ionized. It can carry a charge. And we'll talk about ion dipole attractions later on when they're actually really important for some reasons, okay? And we'll talk about ion-ion attractions in the biochemistry part of the course that are important for the way that proteins fold, for example.
Okay, that makes a lot more sense. Thank you.
You're welcome.
I had two different teachers that taught it different ways, and I wasn't sure.
Well, now you know which teacher was the right one, whichever one it was that didn't put those in the list of intermolecular forces. So you have to have a molecule to have intermolecular forces, right?
That makes a lot more sense. Thank you.
Yeah. So now that we've talked about naming aldehydes and ketones, we've talked about the polarity of aldehydes and ketones and what kind of intermolecular forces they have. So I'm not spending a ton of time on that section on intermolecular forces, because you should already be able to connect in your brain something about the type of intermolecular forces those functional groups have to what they do in terms of melting and boiling points. All right, so since aldehydes and ketones have the middle kind of intermolecular forces, if we compared them to an alcohol about the same size, so for example, what if we had cyclohexanone versus cyclohexanol? Which one of those would you expect to have a higher boiling point between them? Cyclohexanol all day would have the higher boiling point. And the reason why, because they're very similar in size, all right? So we don't have to worry about one just being a lot larger in molar mass, and so having the higher boiling point that way. So they're similar in size, but cyclohexanol has hydrogen bonding as its strongest type of intermolecular forces. So stronger intermolecular forces means higher melting and boiling points. So we don't have to keep on reiterating that like sliding scale of melting and boiling points. All you have to do is remember what kind of intermolecular forces it has. And then if you see that it's next to something that has a different kind, as long as they're the same size, you'll know which one melts and boils at the higher temperature, because stronger intermolecular forces mean higher melting and boiling points, right? Okay. So now let's talk about some reactions of aldehydes and ketones. Now, one of these reactions, believe it or not, we've already talked about, and that is the oxidation of aldehydes. So I'm going to cross these out because this isn't part of our reactions of aldehydes and ketones. What if we had that aldehyde and we treated it with Jones reagent? We already know that aldehydes are oxidized to carboxylic acid by Jones reagent. The reason why is we cannot stop our primary alcohol from going through aldehyde and keep on being oxidized all the way to the carboxylic acid in those conditions. So aldehydes are oxidized with Jones reagent or any one of a crap ton of other oxidizing agents into carboxylic acids. So ketones cannot be easily oxidized any further, because to do that, you have to break carbon-carbon bonds instead of carbon-hydrogen bonds. Now, reduction of aldehydes and ketones is very, very similar in a lot of ways to reduction of alkenes. So when we talked about an alkene like this being reduced, you'll recall that we used H2 and a transition metal like palladium. And that was an addition reaction where we added a hydrogen to each one of those two atoms that shared the double bond. Very, very similarly, we can use H2 and a transition metal catalyst to reduce carbon-oxygen double bonds as well, all right? So we can add a hydrogen to the carbon and the oxygen side of that ketone or aldehyde. And what would that look like? So let's say we were treating acetone with H2 and a transition metal catalyst, and we'll use platinum this time to be uber fancy. Remember, transition metal is not really important. It's a catalyst for the reaction. Platinum, palladium, and nickel are the three most common transition metals to use. Palladium and platinum both work a lot better for carbon-oxygen reduction than nickel does. Nickel's cheap, but it doesn't work as well. So we added a hydrogen here and a hydrogen here in place of that carbon-carbon double bond. What if we add a hydrogen here and a hydrogen there in place of that carbon-oxygen double bond? We reduce our ketone to a secondary alcohol. So ketones are reduced to secondary alcohols with H2 and a transition metal. Now, your book, I think, only don't want to talk about that. Yeah, that's probably pretty good. All right. We will talk about one more oxidation of aldehydes. So we've already talked about this nuclear warhead oxidizing agent that oxidizes basically any primary or secondary alcohol or an aldehyde all the way to a ketone or a carboxylic acid, okay? But this oxidizing agent oxidizes all kinds of stuff. So what if, and we'll get back to reduction because we're going to talk more reducing agents in a couple of slides, but I want to talk about one more oxidation of aldehydes first. So same basic idea, but what if we had both an aldehyde and an alcohol in our molecule? Now, Ariana, we don't have to name this, okay? Don't worry about that. But if we tried to use Jones reagent on this thing, we know that Jones reagent will oxidize secondary alcohols to ketones and will oxidize aldehydes to carboxylic acids. So if we wanted to oxidize both of those functional groups, Jones reagent would be a great choice. But one of the common things that we worry about in organic chemistry is something called selectivity. So selectivity means we want to be selective about which functional group we're reacting with. And there is actually a reagent that is selective for oxidizing aldehydes and leaving alone almost all other functional groups. And the reagent is silver oxide, Ag2O. There are other oxidizing agents that can do this as well. This is a really good example though, okay? The cool thing about this reagent is that as the aldehyde is oxidized, the silver +1 ions are reduced. And when silver +1 is reduced, it's reduced into metallic silver. So in your solution, as this reaction is happening, you form this sort of mirror on the inside of your flask of metallic silver. It's really pretty. It's called the Tollens test for aldehydes. But the cool thing about this is we can pick which one of those functional groups we're going to oxidize. So now that you know what the products of each of these reactions are, what if you wanted to oxidize that secondary alcohol, but not the aldehyde? Is there a way to do that? What reagent would we use to oxidize the alcohol and leave the aldehyde alone? Do we know of an oxidizing agent that oxidizes secondary alcohols to ketones, but doesn't oxidize aldehydes?
Would that be PCC?
It would be PCC. So the cool thing is, by using these three reagents, we get to pick between alcohols and aldehydes which of the functional groups we oxidize. Isn't that really neat? I think it's really cool that we get to like sort of reach in with our hand and decide which, or maybe both of those functional groups that we're going to change at a time. So that's what selectivity is all about, is picking a reagent that only reacts with the one part of the molecule that you want it to and leaves the other parts alone. So it was really important for me to teach you about silver oxide as a selective oxidizing agent, because we're also going to talk about selective ways to reduce functional groups as well. So we've already talked about using H2 and a transition metal to reduce carbon-carbon double bonds to carbon-carbon single bonds. We also talked on the last slide about using that exact same reaction, H2 and a transition metal, to reduce carbon-oxygen double bonds. So the cool thing is, there's actually a reagent that is even more selective for reducing carbon-oxygen double bonds to carbon-oxygen single bonds. The reagent is called sodium borohydride, NaBH4. I'm not positive if your book has that reagent listed. It does not, and that is total lame sauce. So if we're going to talk about selectivity of how we reduce carbon-oxygen double bonds, sodium borohydride is a great example because it is very selective for reducing carbonyl compounds, all right? It's good at reducing carbon-oxygen double bonds, but not good at reducing carbon-carbon double bonds. So if we had a carbon-carbon double bond in this molecule, it would not be touched, but the carbon-oxygen double bond would be reduced. Now, we can actually use the H2 and transition metal as a selective way to reduce carbon-carbon double bonds before we reduce carbon-oxygen double bonds. So this reaction works, but it takes a long time. If we're reducing a carbon-carbon double bond in the presence of H2 and a transition metal, it's a really fast reaction. So if I wanted to, I could use H2 and a transition metal to reduce just the carbon-carbon double bond and leave the carbon-oxygen double bond alone. So we say that sodium borohydride is a reagent that is selective for the reduction of carbon-oxygen double bonds. Whereas H2 in a transition metal is selective for the reduction of carbon-carbon double bonds. Now, H2 in a transition metal can do either one, but it's a lot better at reducing carbon-carbon double bonds. So if we just run this reaction for a short time, we will get done and can stop without having reduced that carbon-oxygen double bond at all. Does that make sense, everybody? So that's a huge topic that we're just sort of like opening the can of worms on today, is selectivity of reagents. And there are only two reducing agents that I really want you to know for this class: H2 in a transition metal and sodium borohydride. But by playing with which one you're going to use, you can actually do a lot in terms of different chemistry with reducing different functional groups in your molecules. All right. So if I just let this reaction with H2 and a transition metal catalyst run for a long time, I could reduce both of those functional groups as well.
So hydrogen on a metal like nickel is selective only for short periods. It's otherwise.
We can, so Ariana, we can control the reaction. So it depends on a lot of things. I'm oversimplifying a little bit. So if I was trying to reduce just the carbon-carbon double bond, one thing that we're not talking about here is how we actually put the H2 into the reaction. Because H2 is a gas, we can either pressurize our reaction container with just like normal air pressure worth of H2, so 1 atmosphere of H2, or we can really like cram a bunch of H2 in there and make it like compressed H2 in the reaction flask. So the difference being, if we have a lot more H2 pressure, that pushes the reaction to reduce more. So if I had 10 atmospheres worth of H2 pressure, that would push the reaction toward reducing both functional groups. Another thing is the time that the reaction is happening. So if you let a reaction like this run for an hour, then you're likely to only reduce the easier to reduce functional group, the carbon-carbon double bond. If you let it run overnight with a higher pressure of hydrogen, then you can reduce both those functional groups with H2 and a transition metal instead.
Okay.
So that's pretty neat about H2 and a transition metal. We can decide whether we're going to reduce just some or all of those functional groups in there. Now, the only way that we can reduce an aldehyde or a ketone but leave carbon-carbon double bonds alone is with sodium borohydride.
Is separating those two products a different method?
You can, most of the time when you do those reductions, you're only going to get one product. You won't get a mixture. So the selectivity is so good that you're only going to end up with one product. Like when you reduce something like, say we were trying to reduce this compound, depending on whether we used sodium borohydride in which case we would be reducing just that ketone. I'm drawing it backwards just because I didn't have enough space. Note that that 2-carbon chain is over here now. Big deal. All right. All I did was flip it over like a pancake. So I would not see any of the alternate product probably where I had reduced the carbon-carbon double bond and not the ketone instead. This is a pretty clean reaction. It's just one product.
Okay.
The same is true if I control my conditions carefully with H2 and a transition metal. I can very easily reduce the carbon-carbon double bond and leave that ketone alone. If I let this keep going for a lot longer, I can reduce the carbon-oxygen double bond as well. All right. So there are a number of things that we can do to make our conditions more vigorous to keep on reducing that carbon-oxygen double bond. It can be a higher pressure of hydrogen. It can be higher temperatures. It can be a longer reaction time, but it's a lot easier to reduce carbon-carbon double bonds with this reagent. So that is selective. We can completely reduce that carbon-carbon double bond and leave the carbon-oxygen double bond alone using H2 and a transition metal.
Okay.
So the last reaction that we're going to talk about for aldehydes and ketones is actually probably the hardest organic reaction that we're going to talk about in this class. So in order to do it justice, I'm going to grab a couple of other colors out of my markers here and try and sort of color code things so that you can see where the parts come from. All right. Go with orange and green. That looks pretty good. All right, that should be enough colors. So one of the weird things that can happen with aldehydes and ketones is what happens when we treat them oh crap, and I immediately like messed up my color coding here. So that's supposed to be green. If I treat an aldehyde or a ketone with some kind of small alcohol in the presence of an acid catalyst, what ends up happening is we exchange both of these carbon-oxygen double bonds in the carbonyl group for new carbon-oxygen bonds to the oxygen of the alcohol. So what ends up happening is something that looks like this. We end up with a product where at that same carbon, now we have two of those molecules of alcohol attached. So we've lost the hydrogen off of those oxygens, but those oxygens and the 2-carbon chains next to them come from ethanol here. And we call that molecule that has basically an ether twice at the same carbon, we call that type of functional group an acetal. We can also form acetals from aldehydes just as easily. So let's try, instead of ethanol, Let's try isopropanol. So remember, we're going to attach 2 of these alcohols by their oxygens in place of that carbon-oxygen double bond. That's what we call formation of an acetal. So what does the product look like? Well, the only thing that changes is those 2 bonds are now 2 bonds to the oxygens of whatever alcohol we put in there. Does the color coding help so you guys can see where the atoms are coming from?
Yes.
It's really hard to tell otherwise, all right? Now, the other cool thing is sometimes we form acetals instead of from just a plain alcohol where we have to use 2 of them. If we use a diol, we can use both of those OH groups and form a cyclic acetal. So what about this? So Ariana, there's your favorite, ethylene glycol. All right. If we use ethylene glycol in a transition or an acid catalyst, we end up using both of those oxygens to replace the bonds to the carbon of that carbonyl group. So it ends up looking like this. It's pretty awesome, actually. If I'm coloring the way that I did for the others, there, that's better. So you guys can see that both of these oxygens form bonds to that carbon that had the carbonyl group.
So it loops around
Yeah,
itself.
we call that a cyclic acetal.
Are these ethers that they're forming?
It's not an ether, and the reason why we don't call it a diether is because ethers as functional groups are not very reactive at all, and acetals are reactive for reasons that we don't have to get into in this class. It'd be inappropriate for us to call these ethers because ethers don't really do a lot, and acetals are very, very reactive in certain conditions.
Okay.
And the cool thing is, all we have to do to get rid of the acetal and turn it back into the aldehyde or ketone is treat it with water. All right, and water and an acid catalyst will give us whatever our aldehyde or ketone is back. So I'm not going to make you guys learn about why being able to turn them back is so important, but one of the reasons that it would be important for us to be able to turn them back is something called protecting group chemistry. So we'll talk about it just as like enrichment, but all you have to know is that if you have an acetal, you can undo that and get the carbonyl group back by just treating it with water and an acid. So let's look at one more of these together. This is my favorite aldehyde in the entire universe. That is benzaldehyde. So benzaldehyde smells, depending on who you are, it either smells like almond extract or cherry extract. It is a very pleasant smelling compound. It's one of my favorites. Orlina, you don't believe me, do you? I saw that little like, it's for reals, all right? So this compound is like my favorite to sniff. I have some in the lab. We don't even really use it for very much chemistry. I just bring it so I can bring a bottle out and like let students sniff it because it smells so good. It's one of my favorites. So what if we treated our benzaldehyde with this alcohol. And an acid catalyst. Note that now there's one more carbon in between those two OH groups. So count your carbons carefully. All right, that was very alliterative. Count your carbons carefully.
So is this the part in chapter 16 where they're talking about hemiacetals that continue on to form acetyls?
Hemiacetals and acetals, yes. We're not
Okay.
worried about hemiacetals because they're not really isolable. We can't stop this reaction halfway through and get a hemiacetal. There are times when hemiacetals form in solution. So that's really important when we talk about what the structure of carbohydrates look like in aqueous solution, because sometimes they're like a floppy chain and sometimes they form a ring by forming a hemiacetal. But we'll get to that later. So don't worry about the hemiacetal version of this in the middle.
Okay. So an acetal is when two oxygens, two ether oxygens are sharing a similar, a
Two
carbon
different
with-
oxygens are bound to the same carbon.
Does it matter if there's a continuation of an R group on the other side of the oxygen from the shared carbon?
Yes. So if it was just an OH group, then that wouldn't be an acetal. It would be either a hydrate or a hemiacetal. So yes, there has to be an R group on the other side of the carbon for each one of those in order for it to be an acetal.
If they weren't sharing a carbon, that's when it would be two ether groups. So if in
Yes,
like that
if they
last
were bound to different carbons, then it would be a diether instead. So if we had something like, it's certainly possible. I don't know that I have ever, yeah, there are definitely. So what if we had something like this? That is definitely not an acetal
Okay.
because our
That was
two
one of my
bonds to
questions
oxygen
from
are
reading the
not
book.
on the same carbon.
Okay. So are those both ethers?
Yes,
So is it like a
it's a diether.
cycloether or a
Yeah, a cycloether, that would be a fine way to describe that.
Okay. Okay, that was one of my questions. So that's perfect. Thanks.
And the reason why it would be inappropriate to call this an ether is because we can very easily turn this back into an aldehyde by treating it with water and an acid. Water and dilute acid wouldn't really do anything to those ethers. We could get the ethers to turn into something else with a really, really concentrated acid solution, but ethers are not very reactive and acetals are super reactive. They're easy to transform back into an aldehyde or a ketone.
Why is that?
Yeah,
Why is
don't
it
take majors organic chemistry. I wish I could teach the majors level course at SVC, but I'm on the island campus and we don't have enough students to run our own majors level organic class. The person who teaches it over at the Mount Vernon campus, she is amazing and has won teacher of the year over there several times. So you should really check it out. It's a good class. Very information heavy, but a really good class. Yeah, that's the biggest thing that I miss about what I get to teach at my new job versus my new job. This is my 4th year here. versus my old job. My old job, I got to teach the majors level organic class, and it was like very dear to my heart. So I miss it a little bit.
It seems like such a little thing to make such a big difference.
It makes a huge difference though. So the reason why, all right, the simple reason why, the 2-sentence reason why, if we're talking about how delta positive the carbons are, having 2 oxygens attached to that carbon makes it extremely delta positive. So that makes that carbon a lot more reactive than either of these carbons that have only 1 oxygen attached.
Got
That's
it,
it.
because the carbons are more electronegative, so they take just a little bit more away from the carbon.
The oxygens are more electronegative.
Yeah,
So they
oxygens
take
are-
electron density away from carbon. So that carbon is very, very short of electron density. That's why it's
Got it.
reactive.
Okay. That's a good short explanation. It's perfect.
Yeah. Any questions about forming acetals? Guess what? We just covered all of chapter 16 in one lecture. That was short. So the cool thing is now you guys are starting to get a knowledge base for organic functional groups, where every time we introduce a new group, it's going to be sort of a similar thing. Here's how we name some of these molecules. Here's what kind of intermolecular forces they have and how we would expect them to stack up in terms of melting and boiling points. And then what reactions do we have to be aware of those functional groups? So every time you study a functional group when you're preparing for a test, make sure that you're thinking about those things. All right. The other thing is now we've studied enough functional groups that I don't feel like I need to go back and talk about what the shape is around that carbon. We've done it already. That carbon right there in the ketone has 3 electron groups. So we know they're going to be 120 degrees apart from one another, and that the shape around that carbon is going to be trigonal planar. We've already seen that shape for a bunch of other functional groups. So why do we have to keep talking about the geometry of every functional group when you already know what all those shapes are? So it's just like after we have enough experience, we can start to take some things for granted because we've seen them a bunch of times before. It should be getting easier, if not now, at some point really soon, where things are going to look more familiar because they look really similar to stuff that we've already seen. Any questions? Okay, so tonight I will make sure to figure out what the crap is going on with our Wednesday recitation from last week, and I'll post it. All right. The other thing that I'm supposed to post, Orlina, what was the other thing that I was supposed to post? I didn't write it down. So
The PowerPoints.
the PowerPoints for the chapters 16 through 19. I'll get those posted.
Wait, I think for this one it's actually going to be 17 or 16, 17, 18, and 21. That's at least what it says on our thing.
I probably can post just all the rest of them for the whole class. That would probably be pretty handy. Then I don't have to worry about it again. I'll just do a big batch update.
Perfect.
Yeah.
That's even better.
Yeah. Any more questions? Yeah. I saw Elizabeth. Thank you for that. I appreciate that. How did you, have I told you guys that I'm a Saved by the Bell fanatic? Did I tell you guys that?
I saw the
Yeah.
news today. That was so sad.
Yeah, it is really sad. He just got diagnosed like 2 weeks ago with cancer.
Yeah, it was like less than a month ago.
Ugh. And what's kind of a bummer is he was like in his 20s, he was kind of a dingus to the rest of the cast, and they had a big falling out. And they were just sort of like mending those fences now, and they never got to like really completely reconcile. At least not that's been made public, but to some extent the cast had sort of started talking to each other again. So yeah, let's hope that they were all on good terms. All right, what time are we at right now? We're wow. We started at 4:30. It's 6. If you guys want, we can do like a little bit more exam review, or if there's any questions from any of the homeworks that you want to go back over. So I've got a little bit more time if you guys want to use it, or if you're like cooked at this point, that's totally okay as well. Any more questions, things that you want to do another example problem of before the exam?
I have a couple more questions.
Yeah, any questions? Let's do it.
If somebody else has questions, you can certainly go first. I've asked a lot, sorry.
I know that my, like, this is probably why I'm ready to take a bunch more questions. I don't normally drink energy drinks later in the day, but I was feeling a little down before class. So I'm like, I'm going to pep that right up. Okay, what do you got? Let's do it.
Does anybody else have questions first?
Is yours exam related?
Not really. I don't think. Really.
Exam questions first.
Yeah.
Sorry. I would like for you to go over the constitutional isomers and that thing just one more time. I'm still just
Yeah.
struggling with
Okay. So constitutional isomers.
it. Yeah.
So when I say constitutional, that root has something to do with like the way something is built. All right. So the US Constitution governs the way that we have built our government. All right. Constitutional isomers are isomers that change the way the molecule is built, the way it's put together. All right. So they have the same, and we're always talking about like the relationship between at least two compounds. All right. So we're talking about how these two compounds are similar to one another. They have the same formula, but different order of attachment. In other words, they're put together differently from one another. So what if we had a chemical formula like C6H10O? What I want you guys to try and do is try and give me 3 different constitutional isomers of that formula where none of the 3 have the same functional groups as any of the others.
Is this the thinking outside the box question again?
Yeah, but it's really not outside the box. It's just in a box that you're not comfortable with yet. So from the beginning, what you should be thinking about is we know that alkanes with 6 carbons should have 14 hydrogens attached to them. All right. So the fact that this 6 carbon molecule only has 10 hydrogens instead of 14 means that we've got 2 different places where we have some kind of an extra bond between carbons instead of bonds to hydrogen. So we should have either 2 carbon-carbon double bonds hanging out in this thing, or a carbon-carbon triple bond hanging out in this thing, or a ring and a carbon-carbon double bond, or 2 rings. All right. Those are ways that we can take away 4 hydrogens. Anytime we take away 2 hydrogens from our formula, we either make an extra bond between carbon and something that isn't hydrogen, or we make a ring. So there's lots of different possibilities here. So one possibility that I can think of is that possibility. So 2, 4, 6, 8, 10 total hydrogens. And if you look, where did those 4 hydrogens go? 2 of the hydrogens went away from our 6 carbon alkane. 2 of our hydrogens went away because of the ring, and another 2 hydrogens went away because of the carbon oxygen double bond. So what other ways could we end up with this formula, C6H10O, where we didn't have a ketone involved? What about that? So count your carbons, count your hydrogens. I see 6 carbons in that formula. And then 2, 4, 6, 8, 9, 10 hydrogens. So that's C6H10O. And we have an aldehyde functional group there. What about that molecule?
That's making sense. Can we shift that into the trans and cis?
Yep. So trans and cis are the one type of stereoisomers that we have to know about. So the difference with stereoisomers is there isn't a difference in the way that they're put together, only a difference in the way that they take up space three-dimensionally. So the classic example of trans and cis isomers are these two versions of 2-butene. They have the same order of attachment because we have a CH3 bound to a carbon-carbon double bond bound to a CH3 in both cases. But because this carbon-carbon double bond can't rotate, these are different compounds from one another in the way that they take up space. So in space, one of them has those, I need to go back farther. One of them has those 2 methyl groups on the same side of the carbon-carbon double bond, and one of them has the 2 methyl groups on opposite sides of the carbon-carbon double bond. So same order of attachment, but they take up space differently. These are a pair of stereoisomers, and specifically we call them trans and cis stereoisomers. That's one kind of stereoisomers. So the 2 methyl groups being on the same side of the carbon-carbon double bond makes this the cis version of 2-butene. And the 2 methyl groups on opposite sides make this trans 2-butene. We can also have cis and trans isomers of much longer alkenes. So this would be trans 2-heptene. And this would be cis 2-heptene. So in this case, the 2 identical groups that are on opposite sides are the hydrogen here and the hydrogen here versus the hydrogen here and the hydrogen here. The fact that those 2 hydrogens are on the same side of the carbon-carbon double bond is what makes this the cis isomer of heptene. Is that helpful?
Yes, it is. Yes.
Yeah, being able to distinguish constitutional isomers from stereoisomers is really important. There are more kinds of stereoisomers than the ones we've talked about in this class. So, for example, it's possible for our 2 OH groups on this molecule to both be on the top side of the ring, or for that one to be on top and that one to be on bottom, or for that one to be on the bottom and that one to be on the top. No one of these 3 is identical to the others, even though they all have the same order of attachment. All right. So if I was naming this This would be 1,2-cyclohexane diol, but each one of them has a different way of those two OH groups occupying space. So these are all versions of, they're stereoisomers of one another. All right. You don't have to know how to handle that with naming, but they are stereoisomers. All right. Same order of attachment, but they take up space differently from one another.
There are naming mechanisms for them, though?
Oh, yeah.
Okay. Okay.
Any other questions? 11 through 14's got quite a bit of material on it, but with all of the video resources you guys have, I think you're in position to do a really good job on this test.
Looking back over.
What time did you say it posts tomorrow?
Starts at 9 a.m. And because something happened with the video, I may actually extend the open exam window all the way up until our recitation on Wednesday. Like, you got to get it done before class on Wednesday. So if you want to take it earlier in the day on Wednesday, that'd be fine with me as well. There's no way I'm going to get them all graded on Wednesday before class anyway, because exams take a long time to grade. So exam 1 will probably get graded this coming weekend, and you'll have your exam grades sometime this weekend.
Question, are you gonna post the recitation from last Wednesday?
Yes.
Because I would love that.
Yeah, absolutely. I'll post it.
I wrote this question down and I'm trying to remember why exactly. It was about esters and whether or not you have to have an R group attached to the carbon in the functional group, or could it be a hydrogen?
So
Had like an example of a molecule that I wrote out. I'm trying to understand what I wrote.
all right, let me see if I can draw some molecules that would make that make sense. Okay. So we know that that is an ester, and that is a carboxylic acid. All right, if we're doing functional group identification. So a carbonyl, where we also have an oxygen with an alkyl attachment, that's the classic version of an ester. All right.
I guess I'm wondering.
Yeah, so you're saying, what if you have something that looks like
an R group off of other carbon?
Is that what you're talking about?
Yeah.
Don't worry about it.
Oh, okay. So is that no longer an ester?
Actually, to be honest, off the top of my head, I'm not positive one way or the other.
Okay, because the book kept saying R groups, but a lot of the times it says R or hydrogens. When it gives an example of a really small one, it just uses a hydrogen instead of an R. Yeah,
you won't get an example like this ever. The chemistry of that would be, I would probably consider this to be an ester. Okay. But its reactivity would be a little bit strange because hydrogen is a little bit less electronegative than carbon. So this carbon would be a little weird in terms of its reactivity compared to this kind of an ester carbon. So anyway, don't worry about something like this. It'll never come up. You'll either see something where you have a carbon on one side and an OR on the other side. That's an ester. Or you'll see a carbon on one side and an OH on the other side. And that is, actually, I would call this an ester. And the reason why I would call it an ester is because it is possible to have a one carbon carboxylic acid. That's a carboxylic acid. As a matter of fact, this carboxylic acid has a common name. It's called formic acid. Ants make a lot of this, either for like defense from predators or some other reason. But anyway, if you've ever eaten an ant, anybody ever tried to eat an ant? I know some people like to eat insects, like it's like one of the in vogue kinds of cuisines. All right. Ants actually taste sort of like, I wouldn't call it citrusy, but it's a sharp taste. And the sharp taste comes from formic acid. So by sharp, I mean like, you know, like vinegar has that sort of sharp note to it, or oranges from citric acid. So all those are carboxylic acids. So the sharp taste that you get from ants is their formic acid. It's not unpleasant, actually. It's a nice acidic note, particularly if you cover your ants with just a little bit of chocolate. So chocolate covered ants have a nice like counterpoint of that acidic note along with the mellow chocolate flavor.
Eating insects isn't that weird when you consider seafood. I mean, shrimp are basically sea insects is all.
Yeah, but they're a lot meatier than ants are. I think that's why a lot of people haven't tried insects, is because there's just not that much food in each individual one of them. And some insects legitimately just taste gross. I know there's some creatures that eat.
I don't
like,
do insects. Like they crawl and they're gross and they just ew. I'd like shrimp. Okay, I can understand that. Like they kind of do the same thing, but like
they do exactly the same thing.
But I don't see that physically. Like I'm not underneath the water to see them scurry across the floor or go up my wall or.
What about crabs?
Whatever
crabs do the same thing, and you know they do because they can't really swim very well.
Never caught.
I have a question. Do insects have a lot of collagen?
I actually don't know off the top of my head. I know that insect shells are mostly made of chitin, if I'm remembering right. So chitin is the same stuff that shrimp shells are made of. So I think that like lots of things that have exoskeletons are made of similar stuff.
I have a question about the paper in front of you.
Yeah.
Formic acid, so it's not an acetyl because of the double bond. But if it didn't have a double bond,
that's not an acetal, it's a carboxylic acid.
Okay.
You can have a one carbon acetal. So for example, what if we took formaldehyde and treated it with, this is not on exam 1, we just learned about acetal formation today. If we took formaldehyde and treated it with ethanol, then we would end up with something that looked like this. So I'm drawing that in a special way so that you can see that this carbon and this carbon are the same one. I'm not color coding it anymore. I'm trying to, what's that?
I thought you were drawing it to make it look like an ant head.
No.
Okay.
No, I'm just trying to draw it in a way where you can see where the carbons are coming from. And if you need it color coded, then.
And that's where if you treat it with water and the acid again, it'll go back.
Yep.
Okay.
Although I have no idea why you'd ever want to do that with just formaldehyde, but you could. Okay, folks, any more questions from exam 1? So I will post the recitation from last Wednesday. I'll post the remaining PowerPoints for the course. And I'm going to extend the exam window all the way up until recitation time on Wednesday. So if you have time in the morning on Wednesday, you can take your exam anytime before class, but it has to be finished before 4:30 on Wednesday. And that's no big deal to me because I'm not going to get them all graded before recitation on Wednesday anyway. It's not like if if the exam window closed late on tomorrow night, It's not like I'm going to stay up until 4 in the morning grading those tests to get them back to you by Wednesday. That's not happening. I love you guys, but not that much. All right, any other questions? I do have office hours tomorrow, so if you haven't started your exam tomorrow and you have a quick question, I'm happy to help you out with something, but I can tell if you started your test, so I won't help you if you already started. Other than that, no lab for this week because of the test, so we'll start up another lab next week.
And for those, are you gonna have those up as well
Yes.
in the next like day or so?
Yep. I'm working
Okay.
on it, Orlina. I'm trying to stay ahead of you guys.
It's totally all right. I'm just wondering when it would possibly be
Crafting a
posted.
new class online from scratch is like, it's a ton of work, and I'm doing my best, I promise.
Husband had to do that, and he spent quite a few hours.
Yeah.
Just in
It
the
literally
preparation.
takes me
That
more
was
than
like
twice as long to do my job now than it did when I was in person. It's insane.
Yeah, it took
I'm
him
almost
days.
I'm almost wondering, is it for like the reading quizzes, is instead of having them like answered, is if like people don't quite understand, if you post the questions, which what you would do, and then just have somebody write it down on a piece of paper, if then like if they come into office hours and
Yeah, I
discuss
know,
it a
but
little
then
bit
there's
with you?
not, well, two things. Then that's another thing that I have to grade 48 more of every week, and it's not auto graded. And also the whole point of the reading quizzes isn't the grade, because it's like a trifle worth of points anyway. The whole point is like instant feedback, right? That's why I
Yeah.
want those reading quizzes there, just to give you a little practice where you get instant feedback if there's something wrong with the answers.
Right.
And there are other mechanisms that we already have in the class for that. The homework assignments in the back of the book, all the odd numbered exercises, answers are there anyway, so you can check your answers. But if there are no points attached to them at all, then people don't do it. So I'm just trying
Right.
to give people a way where they're forced to look at feedback. It's just not working very well right now.
Okay. I was just trying to think of like a slightly easier way, as in maybe not having them graded, but being able to like talk to you about it that way.
So that's the practice exam, right? That's not graded. You don't have to do it if you don't want to at all. But there's a lot of practice questions that are very, very similar to the level of difficulty of the real exam, which is all written, by the way, now. I know everything that's going to be on it.
Sweet.
Yeah.
Are there any paragraph questions?
I actually don't know off the top of my head. I wrote it, but it's been a few days. I can't remember if I put anything where you had to write. I think there may be something where you have to define things in your own words, but I don't think there's any paragraph questions in there.
Okay.
All right. Anything more? Study hard. Exam opens up tomorrow morning. The instructions will be in Canvas. If you have any questions, text me. All right. My phone number will be right on the exam instructions, and I'll be around, so I can give you feedback if you need it. Okay. But I'm not going to tell you if you're doing something right or not. I can't help with that, but I can help if you don't understand something. All right. Have a wonderful night, you guys, and I will see you on Wednesday.